Question 21 from the 2025 Higher Physics Examination from the SQA, and it's paper 1. A 7 ohm resistor is connected to a cell as shown. The internal resistance of the cell is 3 ohms. The switch is now closed. The reading on the ammeter is 0.15 amps. And we're asked to find which row in the table is going to give us the EMF and the reading on the voltmeter. Now the EMF is going to be the sum of the voltage dropped across the internal resistance and also the terminal potential difference, which is the voltage dropped across here. So we can find the EMF. And the reading on the voltmeter is just simply going to be the same as the reading across the 7 ohm resistor. So let's do our method. We look at each component in turn, put down V, I and R, and for the 7 ohm resistor V, I and R, and fill in as much things as we know. We know the internal resistance is going to be 3 ohms, and we know the current flowing in the circuit once it's closed is going to be 0.15 amps. So we know that there then. So we can work out and find the voltage across the internal resistance right away, and we can do that at the side of our page. V is equal to IR. We'll get one thing missing, it's the voltage, so we can work it out. So we've got 0.15 amps, and it's going to be multiplied by the resistance, which is going to be 3 ohms, and we're going to get a value there of 0.45 volts. So we know that we're going to have 0.5 volts across the internal resistance, so we can mark that in there and complete that little table. 0.45 volts. Now concentrate on the external resistor, the resistor connected to the terminals of the battery. We know the resistance is 7 ohms. We know the current is exactly the same around the circuit, 0.15 amps. And therefore we've got a simple case of working out V equals IR again. So V equals the current going through the resistor times the value of the resistor. The current is going to be 0.15 amps. Multiplied by the resistance, which is going to be 7 ohms, and we work that out, we get a value of 1.05 volts. And we can fill that in as well. So now we've got completely everything we want to know about that circuit. We have got the loss volts, we've got the terminal potential difference volts, and we can find the EMF now. So the EMF is really the sum of these two potential differences. Remember the EMF E, you're going to lose volts here and lose volts in this resistor here. So we just add up what we've lost. So for the internal resistance, 0.45 volts, plus the voltage down here across the resistor, 1.05 volts. So if we add that up, we get a value of 1.5 volts. So we know the EMF is 1.5 volts, and we do know that the terminal potential difference, this voltmeter up here, is going to read exactly the same as the potential difference across this single resistor here. You can see the resistor connected to the end of the voltmeter. So the voltmeter reading here will be exactly equal to 1.05 volts, same as the external resistor. So we're looking for an EMF of 1.5 and a reading of voltmeter to be 1.05. That's going to be response D. Question 22. A battery has an EMF of 12 volts and an internal resistance of 0.40 ohms. Two identical resistors, each of resistance R, are connected to the battery as shown. And the reading on the ammeter is 4 amps, and we've got to determine the value of that resistance. Well, when you see two resistors in parallel with the same value, you know that the combined resistance is going to be half that value. So we can replace those two resistors with a new resistor with just half the value. So we can write that in there. The new resistance is going to have half the value, which is going to be R divided by 2. Now, the same technique we did with the last question, what we do is we make up our little labels for each one. We have got V, I and R. And this resistor here, we've got V, I and R as well. Now we're told that the current going through the circuit is 4 amps. So we've got 4 amps here. We've got a resistance of 0.40 here. So therefore we can go ahead and we can work out what the lost volts is by going over here and saying that lost volts V is equal to IR. Very similar to the last question. Is going to equal to the current, which is 4 amps. Multiplied by the resistance, which is going to be 0.40. So we've got that there like that, and that gives us a potential difference of 1.6 volts. So we can fill that into our list. The voltage across the internal resistance, or the lost volts, is going to give us a value of 1.6. I'll just drop that wee bit out there. 1.6. So V equals 1.6 volts. Now our list down here, we know what the current is. It's going to be 4 amps. We know what the resistance is. It's going to be R divided by 2. R is what we're going to try and find. And we need to find the potential difference across this resistor. But if we know we've got 12 volts for the EMF and we've dropped 1.6 volts here, then we can find out that the voltage across this resistor is just simply going to be 10.4 volts. Because we've got 12 volts, lose 1.6, you're going to have 10.4 volts available here. So we have calculated everything here except the value of R, and we know we can work out what R is, because R is simply equal to the voltage dropped across the resistor divided by the current going through. And we can put in our values. V is going to be 10.4, so we can put that in, 10.4 volts, divided by, and I is going to be 4. And therefore, we've got the following equation. The combined resistance R, as we know, is going to be R upon 2. So R upon 2 is equal to 10.4 divided by 4. And therefore, if we multiply through by 2, we get the value of the resistance is going to be 10.4 divided by 4 multiplied by 2. And a wee bit of cancellation, and we have R is equal to 22 goes once, 24 goes twice, is going to be 10.4 divided by 2. And that brings us to an answer of 5.2 ohms. 10.4 divided by 2, 5.2 ohms. So we've now got the value for the resistor, and that's going to be response number, a letter E. Question 23. A student makes the following statements about red and blue LEDs. LEDs are light emitting diodes. And the 3 statements are the following. The first statement is the gap between the valence band and the conduction band is larger for red LEDs than blue LEDs. The second statement is red LEDs emit photons of longer wavelength than blue LEDs. And the third statement, the potential difference across an LED determines the wavelength of the photons emitted. Now the first thing we have to do is establish which colour has got the longest and shortest wavelengths. And we know that if we're looking at blue light, we know that blue light has got the short wavelength. So blue photons have got the short wavelength. So we can mark that down, short wavelength. And red light has got the longest wavelength. So red light has got the longest lambda. So we look at the statement 2. It says red LEDs emit photons of longer wavelength than blue light. Then this statement here is correct. So we'll just make that little tick there for that one. That's correct. Now let's look at the actual semiconductors. And we bring those semiconductors in, we can see 2 semiconductors here with different energy gaps. And we know how a LED works. An LED works because we have got the electron, which is in the conduction band, will fall down the energy gap into the valence band, meet up with a hole, and produce a photon of light. So the same here, we have got the electron falling down a bigger energy gap, and that's going to release a more energetic photon. So we can just write underneath this one here, the photon emitted here, the photon is going to have a very low energy. So low energy photon because the gap is very small. And this one here, the photon is going to have a large energy gap. So energy is going to be high for this one here. Now, that's what's got here. So let's see, we've got the statement 1 says the gap between the valence band and the conduction band is larger for a red LED than for a blue LED. Well, we have to look at the equation for this one, and the equation for any photon is energy equals h times the frequency. Now we know that the frequency is equal to the speed of light divided by the wavelength, and therefore we can change this equation here into its sister equation. We can say energy E equals h and swap over the frequency to give us c upon lambda. This gives us a relationship for the energy and the wavelength. So we can see for a low energy we must have a big wavelength, a big number divided into this is going to give us a low energy. So that's going to correspond to the very long wavelength. So it's going to be the long wavelength one, which in fact is going to be the red LED. And similar argument for this one, you've got a bigger energy. A bigger energy must mean a smaller number at the bottom. It means a smaller wavelength. So you've got a smaller lambda of photon given off here, and that must mean it's going to be the blue light, because remember, blue has got the smaller wavelength. So that's all us established, all our theory. And for statement 1, it says the gap between the valence band and the conduction band is larger for red LEDs than for blue LEDs. Well, that's going to be wrong, because we know fine well that the red LED is going to have the small energy gap. So that one's going to be wrong. That just leaves us with the third statement, and it says the potential difference across an LED determines the wavelength of the photons emitted. No, the only thing that determines the wavelength, the colour of the photons emitted from this process, is the energy gap itself. If you've got a small energy gap, you have a photon of small energy, which means longer wavelength. If you've got an energy gap of a big energy gap, you're going to have a transition. We're going to give off a photon of smaller wavelength to satisfy the equation E equals hc upon lambda. So this last statement is actually wrong. So what does that leave us with for a response? 2 only, and the answer is going to be B. Question 24. A student measures the acceleration of a toy car down a slope. The experiment is repeated and the following values of the acceleration are recorded. And the student has repeated the experiment 5 times, because you get 5 sets of data there. Which row in the table shows the mean value of the acceleration and the approximate random uncertainty in the mean value of the acceleration? Well, the first step is to find the mean value of the acceleration, and that's found by adding up all the numbers which we have, 0.28, 0.29, 0.34, 0.30 and 0.29. If we add them all up, we get 1.5 meters per second every second, and we're going to divide that by how much data is there, which is 5, and we're going to therefore have a mean value of the acceleration to be 0.30 meters per second every second. I put in 2 significant figures here. Now, to find the random uncertainty is just simply go to the maximum value we have in the data set, take away the minimum value, and we're going to divide that by how many data parts we got here. So we have the maximum value here, and the maximum value is going to be, in this case, 0.34. So 0.34, we'll just leave units out for the moment. Take away the minimum value, and if you check your data, the minimum value is got to be 0.28. So we're taking away 0.28 and we're dividing that all by 5. So if we do that on our calculators, we get an answer of 0.012. Now we can put that into the same number of decimal places. 0.012 becomes equal to 0.01. So the random uncertainty will be plus or minus 0.01. So let's check out what part of the table we have. We're looking for a mean of 0.30, which could be this one or that one, and the random uncertainty is going to be 0.01, which is this one here. So our response is C. Question 25, the last question from paper 1. A black hole can be formed from a star which has become so massive that it collapses under its own gravitational force. The radius r of a black hole is calculated using the relationship r equals 2gm over c squared. And it tells us what these symbols mean. G is the universal constant of gravitation, which we can look up in our data sheet. M is the mass of the star, which we're told is 1.99 times 10 to the power 31 kilograms, and C, of course, is the speed of light, 3 times 10 to the power 8. So all we have to do here is be very careful with calculation and put in our numbers into the formula. So we have the following: the radius of the black hole r is going to equal 2gm, which is going to be 2 times the universal gravitational constant, which is 6.67 times 10 to the minus 11. I'm going to multiply that by the mass of the star, which is 1.99 times 10 to the power 31. So that's our top calculation. Put that in a bracket, and we're going to divide that by the bottom number, which is c squared, which is 3 times 10 to the power 8 all squared. It's a simple calculation, but you have to be very careful putting it into your calculator. Make sure things are put in right. Do it twice so you get the right answer. You can check your answer. And the answer I get from here is on the calculator would be 29496.2. And it's going to be meters. Now I have to put that into significant figures, so we're going to work with 3 significant figures. So we'll go to this one here. It's going to be 2, 9, and because 4 and a 9 after it, we'll call that 5, and we'll have 2 nothings after it, like that, meters. We can put that into our standard form, scientific notation, 1, 2, 3, 4, and it's going to be 2.95 times 10 to the power 4 of 10 to the power 4 meters. That's the radius, which will give you the black hole. And let's check our responses, and it's response C, and that finishes this paper. Our answer is going to be response C.